Okay, today's topic is presented by Rofan, and he is going to introduce us with some adversary sample attack methods. Okay, Rofan, please start.
Okay. Good afternoon. Today I will introduce some state-of-the-art adversarial attack methods. This is the overview of my presentation. So first, what is adversarial attack? Mathematically, we want to find a transformation A to transform input image x0 to x, where x is our adversarial example, such that x is misclassified as class T. Most of the state-of-the-art adversarial attack adopt additive attack, which means we find a perturbation R, then we add back to x0. That's how we obtain x. So what is the goal of adversarial attacks? There are two goals. The first one is we want the perturbed image to change the label. So hx is the classifier. Secondly, we keep the perturbations to be small. So we want the distance between x and x0 to be small. From now on, all the adversarial attack we are going to discuss today should follow these two goals. Given these two goals, there are three ways to formulate adversarial attack. The first way is called minimum norm attack. It finds x by solving the optimization problem. The objective function is to minimize the distance matrix between x and x0. So this is to control the amount of perturbation. The constraint is to keep the maximum classification score for any class J, which is not class T, minus the classification score for class T to be less than or equal to 0. So the interpretation is that we want X to be classified as class T. So the classification score for class T, which is GTX, should be larger than any other classification scores. Okay.
So here is going to maximize the number. So you mean that
minimize
the constraint you can it says the here is maximized here.
Here is because we will have a set of classification score, right? So this is the score for our adversarial target.
What does this I means? What is I? I is a label or is a class, right?
This is the J's entry of the classification score vector.
Okay.
Okay. So the max is just taking the maximum classification score other than class T, and we want this to be higher than any other class. So which makes this constraint to be non-positive.
I understand this mathematical notations. I just feel a bit weird because when we apply adversary samples, usually this formula is served as an objective function.
Yes,
right?
That will be introduced later.
Yeah, so I just feel that the objective functions and the constraints are just a little bit switched.
They are actually equivalent.
So you mean it's more it's more
There's
like
just different ways to formulate these two goals.
Yeah, so it's more like a Jew problem, right? The Jew problem. And anyway, if you have the problem, so Ruofan is now introducing the background. If anyone is not familiar or have some questions, for example, Changlin or Nima, if you do not have the basic or some terminologies, you can just raise questions me. So I think we can just wait, and any interruption is welcome.
So the second way is like what you mentioned, we flip the objective and constraint. So now the objective function is to minimize this difference in classification score, and our constraint becomes we keep the perturbation to be less than or equal to eta, so we explicitly control the perturbation. But you can see that in the second way, you need to choose an appropriate eta. But in first way, you don't need any hyperparameter.
Yeah. So I mean, the definition 3 is actually more convenient for the optimization. So, or it do not requires a
Is
new
it?
hyperparameters.
Uh,
I'm thinking
the
that
first one.
these two problems are of the same semantics,
Yeah, yeah,
right?
yeah.
But how does additional eta come from? So I'm just thinking about this problem.
We need to use some prior knowledge. For example, we set it to be 0.5 if
I
the
understand.
x is,
So,
yeah.
but as you described, the definition 3 does not require an eta,
Yes.
right? So we do not, why giving this to equivalent, if definition 3 is equivalent to definition 4, and why definition 3 does not need a hyperparameter? Did you get my point? Hello, Rofan.
Because here we put the distance metric into the objective function, but now if we put it into the constraint, then we have to set some inequality. So that's why we need a hyperparameter here.
Okay. Maybe we do not linger on this problem for now. Please proceed. Thanks.
So the third way is just to combine the two expressions together inside the objective function, and there's no additional constraint. And these two terms are combined by a trade-off term, lambda. Okay, so we jointly minimize both expressions.
So here it looks like a single optimization problems,
Yes.
but it's more like multiple. We just merge two individual optimization goal into one, right? So when we do this trick, we might introduce a risk. So for example, suppose the risk is that sometimes we will keep optimizing this one. Is that possible? We keep optimizing these ones, and we forgot about this to optimize this component, so that the final images is not that relevant. So it will have a huge difference from the original image. I mean, the adversary samples has a huge difference from the original.
Yes.
One.
So these two goals are actually conflicting with each other. So we need to choose an appropriate lambda. So if you think the second expression, we keep optimizing it, then we decrease lambda. So now we focus more on the first expression.
Okay.
Okay. And it turns out that if the eta in the second way and lambda in third way are chosen properly, then these three formulations are exactly the same. So now we have seen the mathematical formulation of adversarial attack, but what is the graphical interpretation of it? So from the above tree formulation, we can say there are two important expressions that frequently appear. So first one is nothing, just the distance between x and x0. We can choose L1 norm, L2 norm, and L infinity norm.
Wait, so infinite. So I still have infinity norm here. So infinity norm is.
So we take the maximum value.
Corresponding here, right? Okay. So I remember that, but I somehow forgot. What is L3 norm? How do we calculate Ln norm?
Is the sum of, for example, you have a vector A, the A. This is the LP norm.
I see. So when it was taken the infinity, okay, so it will just take the maximum.
Yeah.
I see. So if you take the maximum, it's x zeros.
So we are controlling the maximum of the perturbation.
Let me see. Let me think about the shape. The shape that is x minus x1 x. So how? So the distance is between
between.
So okay. So somehow the y. Let me think. So in these topics, and how does the x-axis and y-axis represent?
So suppose x is a two-dimensional vector, and we put x0 on the x-axis, and the blue curve is the. So if 2 points are, if 2x1 are on the same blue line, then their distance are the same. Yeah.
Their two norms are the same.
Yeah.
So somehow this portion is a distance, right? And how about this one? So this portion is still the distance?
Yes.
Okay.
Oh, the distance. Yes.
Distance, so the maximum. So how do we, this is dimension. So but the problem is that this one dimension is not very clear, right? Because this is just one dimension. We can have
I think this graph is not, it's not clear. So yeah, we can just forget about this representation.
Okay, we do not link on this here. Okay, please go on.
Okay, so for the second expression, if we let the second expression to be 0, then it's just the decision boundary. Okay, so graphically, if we move x0 to x, then x actually crosses the boundary and jump to gamma. And gamma is defined here as it is where this equation is less than or equal to 0. And gamma is just the region of class T. So yeah, this is just the boundary. Yeah, please go on. Xiaoling, is Xiaoling there?
Yes.
Do you understood this diagram? Do you understand this diagram?
Yeah.
Yeah, so somehow when we do the visualizations, we somehow need to visualize this more in this space. But this graph is very much like what we would like to do to evaluate to the deep view. So it's more like we started with that point here, and then when we do the move, we move it here. But so our visualizations can support adversary sample generations and active learning, so that is all possible. As long as we would like to move some points in the plans, our visualization can play a role. Okay, please go on.
Thus, the graphical interpretation of adversarial attack is just to project the example onto and beyond the classification boundary. Next.
Wait. So the last sentence.
Project x0 to the classification boundary and maybe U.
Why are you using the word projection? Projection is more like to converting a samples from high dimensional to low dimensional space. It's more like a moving, right? You are moving or
yeah. So here you also move it, and you move it such that this trajectory is vertical to the decision boundary. So that is the minimum distance to move. So yeah, it can also be called like projection.
Okay.
It's just project a point to a line.
Okay, but the actually does not necessarily mean that the adversary will have to be located along the boundary.
Yes, you can go beyond the boundary. So next, let me introduce the attack methods from the tree formulations. For the minimum norm attack, let's first simplify the scenario. Suppose we use the L2 norm for the distance matrix, and we use a binary linear classifier. That is, my gx is equal to some weight vector times x plus b. And we have only two classes, one boundary. So it's either gx less than 0 or gx larger than 0. Okay. Now, given the point x0, it's not hard to see that the optimal perturbation R is just the distance to the classification boundary, right? So in other words, Rx0 is defined in this formula. So this is just a formula from formula of the distance from a point to line. So in fact, for any linear classifier, Rx can be solved by this optimization problem. Okay, but why is that?
No, wait. I would like to. I would like to someone to digest it. So here, so Rx is a vector pointing towards the boundary.
R is the perturbation, right? Oh yeah, it's pointing towards the boundary.
And this one you, so it was subjected to. So for now you would like to minimize the length of R.
It's just here. It's the same as the objective here. So minimize the perturbation, and R is just x minus x0, right?
So but you have to, you have to make sure that it have at least locate to the boundary.
Oh yes.
Right. So this formula means that gx R. What does this R mean?
R is the perturbation. I will explain here.
Okay. Okay, maybe you keep going. I should stop interrupting you.
So the objective is the same objective, but the constraint looks a little bit different. But we can actually simplify it. So in our case, gx is a linear function, right? So we can plug in the formula of gx here. It becomes this. And finally, we get this gx0 plus r. And gx0 plus r is what? It's just the adversarial example. So if we let it to be 0, then it just means the perturbed image is on the boundary. So this is just a mathematical expression for this sentence. Okay, so it's nothing new here.
So here the gradients. So here the gradients towards x, all right. So here the gradients is that the gradient presentation of this formula towards R?
Towards x.
Towards x.
Yeah.
And plus R.
No, just towards x.
Times R.
Oh yeah, times R.
The gradient.
The gradient is just the weight vector.
And so why here the transpose?
Because when you represent a vector, it is by default a column vector. So when you take the dot product, you need to put the transpose in front for the front vector in order for it to get the dot product as a scalar.
So let plus b t equals. Okay, so So this formula is actually expanding result of this formula, right?
Yes.
So we basically we should start with these ones, but it just reverse induce the formula here. Okay.
Okay.
And what does this formula give us? So now we have a conclusion that we
Okay.
have these formulas, and what can we get?
I will explain later.
Okay.
So we have proved that this optimization makes sense, but how do we solve it? We can solve it using Lagrange multiplier method. Do you know Lagrange multiplier method?
Somehow you need to refresh my memory. Maybe you can ask some other students, anyone who still remember Lagrange multiplier method. Anyone who is familiar with Lagrange multiplier method here? Nima, do you remember this one?
I've seen this, but I don't remember actually.
Okay.
I just learn about this. So
okay, that's
if
great.
you have constraint g x0 plus blah 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 equals 0.
You can do the annotations on the screen.
So basically, if you have constraint equals to a constant, for example 0, and then you can times a lambda in front, and then you minimize this constraint. So this
Yeah, because this is equal to 0, so you add this term doesn't change the optimization function, right? So then you take partial derivative equal to 0 to solve this minimization problem. And then finally you can get Rx is equal to this.
By solving this system, are you taking like the saddle point of the Lagrangian? Are you taking the saddle point of the Lagrangian by solving the partial derivatives equals 0?
Oh, sorry, Docking. Did you get?
I just a little bit off mind. So Nima, would you please rephrase your question again?
Yeah. So basically, by taking the partial derivative equals 0, it's like in the resolution process, getting the saddle points.
So it's get a saddle point to minimize a convex function. Yes, it's a way to minimize the convex function. So we just set the first derivative to be 0. For example, a typical example for convex function is the quadratic function. So at the minimum point, the partial derivative is just 0.
Yeah. Okay.
Yeah.
Thanks.
Okay.
But how do you know that it is a global minima, not a local minima?
Maybe for this optimization, it's convex, but I don't know how to prove that it is convex. But this term should be convex, right? At least this should be convex.
So here, so for the Lagrange method, and so the parameters, so that means x is fixed, and we need to find a lambda.
And R.
And
so
R is the perturbation direction, right?
Yeah.
And then R is the vectors leaving from the existing x0. So I still try to digest the logical relations between. So what's the goal here? The goal is that we need to minimize this one.
Yeah, so we want to solve this optimization to get what is the optimal perturbation to use. So we want to express it. We want to calculate it. Okay.
So the goal here is to giving these vectors is zeros, so it will calculate the lambda. So the ultimate goal is to optimize this one, right? Because this one we know this all because equal to 0.
Yeah.
And when we add a 0 values here, what's the benefits we have here?
So we combine the constraint with the original optimization problem.
I understand. So this is original optimization problems.
Yeah.
And
that's how we combine.
But the problem is this one is 0.
Yeah.
And what's the point to?
We want to express R in terms of what we have. What we have is x0, right? X0 is known, J is known.
Okay. I think, for example, we have a boundary like this, and every point lies on this boundary can make the equation to 0, but we need to find, like for example, this is x0, and then we need to find the minimum R.
Okay, sure. That will be very clear. Thanks, Xiangling.
Oh, this is my proof here, but I just skip the.
So back to the proof. So what the proof means?
I'm just solving this Lagrange multiply method. I'm just solving the partial derivative equal to 0. Yeah.
The partial derivative to zeros here. So the point is that you want to prove the partial derivative to be zeros, and it will fulfill our optimization goal.
I want to prove this conclusion that Rx0 can be actually expressed as minus Gx blah blah blah. Yeah.
Okay, please go on.
Okay, so for any linear classifier Gx0, the optimal perturbation is actually can be expressed by this equation. However, the decision boundary for a neural network is usually not linear, but we can assume it is linear around x0. And also we do this perturbation iteratively. And one day we hope we will reach the decision boundary. So this attack method is called deep fool. The idea is just to project the example onto the boundary. This can also be extended to multi-class cases. It's just that we need to choose one boundary to project onto, and we will choose the nearest decision boundary. Okay.
And for these algorithms, how do we choose the nearest boundaries?
I think is here.
So will you please illustrate us the algorithms a little bit?
Okay. So for all the class, we compute the WK prime and FK prime. Then we choose the minimum of it. Oh, I think I didn't take a closer look for it.
So here,
but I think this step is trying to find the nearest boundary.
Okay, please go on. So the idea is here that given a sample X and a given a classifier, you would like to generate a set of perturbation. So So here the perturbation hat is a set of perturbation or only one perturbation. One perturbation, right?
One
so
perturbation.
it always finds the close. So it always finds the close boundary. Just find the close boundaries.
Yeah, just
and
find
try to calculate the
distance.
perturbations or the directions towards the boundary. Okay.
Okay. And for the second formulation, maximum allowable attack, let's again simplify our problem. Let's say we take the distance matrix to be infinity norm. And also we take Gx to be a binary linear classifier. So after the simplification, this optimization process becomes this.
So why do you modify it into B?
Because I'm introducing one of the state-of-the-art attack. So that's the way how they modify the allowable attack. There's no reason. And it can be shown that the solution for this optimization problem is the optimal perturbation is minus eta times the sine of W. So the proof is here. Because x is equal to x0 plus r, so W transpose x plus B can be expressed by this. So we just expand x. And because x0 is known to us, we can define a constant B0 is equal to this to avoid all the constants here. So the optimization can be rewritten as we want to minimize W transpose R minus B0 subject to the constraints. So here we use the
But the problem of XWP, this B is defined, right? This B is constant.
Yeah, this is the constant.
This is constant B. So you would like to B0. So that means you make B, you transform the B into such a value, right? So to simplify the formula to make sure, okay.
Because we are not interested in the things here, once we know the x0, we know all the things. We are just want to know what is the optimal value for R. Okay, and here we use a lemma called Holder's inequality. Don't need to know the details. It's just it can find the lower bound for W transpose R because we want to minimize, so we need to find the lower bound. The lower bound is of this form, and we can show that the lower bound can be attained when R is equal to minus eta times the sine of W. So thus we prove that the optimal R is just minus eta times sine of W.
So here the point. I somehow lose the point. So here, what's the point here? So when you have the conclusions.
The point is to derive this FGSM attack. So just to explain why it is an optimal way.
And where does J come from? So you now you get to definition 7. So
J is just a classifier. It's just a classifier, right? So here we express the classifier as J, but here we express it as capital J. And the derivative, when the classifier is just a linear classifier, then the derivative is just W. So it's the same as here, sine of W.
The function psi, what does this function psi represent?
Just represents the direction of W.
Just the direction. So the sign is the direction.
Yeah. Psi means the direction.
W is actually a vector, right?
It's the weight vector, right?
It's a weight vector. And what's so the sign vector, how do you calculate the sign vector? So can you raise an example here?
Here the sign vector if W, for example, is a scalar and it's equal to 1, then sine of W is 1. If W is 1 minus 1, is minus 2, then sine of W is minus 1.
So it will remove all the scales of W. It just leave the sine of each dimension.
Yes, so it's the direction.
If this direction, so will you please go back to, so here the tag data points, so let's go back to the question here. So if we would like to derive x from x zeros, and the eta is the linear rate, right?
Yes.
And it just keep the sign. It just keep the sign
Yeah,
here.
just keep the sign. So eta is the linear. Yeah.
So that will towards the maximum.
Yeah.
So suppose the boundary is like this, and I will suppose this, and let's make it as a 2-dimension, right? So from now on, from giving this point x0, and clearly the best way to optimize is in this direction, right?
Yeah.
And giving a signs, the signs will either be on the diagonal, this one, we will be on 8 direction, right? And I will highlight this, and this direction is the best, is the fast way from x0 to the boundary. And as you mean, and if it is sine W here, it will only exist in on 8 direction, giving this 2 dimension.
Sine of W. So for example, this is Wx plus B.
Yeah.
Then W is plus 1. So
Yeah.
x will go to this direction.
So it means that it is the farthest way.
Because here it is different from the minimum attack. So here we don't find the minimum distance, right? It's slightly different. Here we don't put this into the objective function. We just keep the maximum of it to be less than or equal to eta, and that's all. So we don't guarantee that this R is the minimum one.
Okay. Okay.
Okay. So here comes the third formulation, regularization-based attack. So there is one state-of-art work that is based on this formulation, which is called CNW, but it has some slight modifications. Firstly, it uses L2 distance for the perturbation. And secondly, you can see we add a margin. We add a margin minus kappa here. So when GTX is enough salient from the rest of the class, then this term will be enough negative. We do not further optimize. Okay.
Does kappa is greater than 0?
Kappa is greater than 0. Minus kappa is less than 0.
So that means it should be, so suppose the kappa is very large. So a successful adversary must be away from the boundary.
Yes.
So in this case, I think Zhangchen is Zhangchen here. Hello, Zhangchen. So maybe Ruofan, you can inform Zhangchen here that when he do the experiment about to see whether the adversary samples will lie alongside the boundaries, we can also set the boundary. So as long as we got this part of adversary samples, and we can always force the successful adversaries away from the boundary. Please go on.
Okay, so that's the main part for adversarial attack, but I would like to discuss several more points here. So first, you may be wondering, are there other types of adversarial attacks? And yes, there are many. And many of them do not require such a complicated math optimization procedure. For example, GSMA. So GSMA perturb one pixel at a time. They choose the most sensitive pixel that can change the classification score the most and change this pixel to 1. So increase it to the maximum. And also we have GAN. So this GAN will generate adversarial examples by another network. So the methods we discussed above are all for white box, which means we know the model's weight. But what if we know nothing about weights? Does random attack work? In white box adversarial attack, it often takes of this form, x equal to x0 plus lambda w. So w is the weight vector, right? If the direction is generated from a random number, suppose r, and r follows normal distribution with mean 0 and covariance matrix of identity, we will have x equal to x0 plus some learning rate times r. Okay, so let's again raise the example of linear decision boundary. Suppose my x0 is here, this here. And now we generate r, but this r should be pointing towards decision boundary, so it should be pointing towards the right direction. Then we only have half chance of successful attack, right?
Yeah.
So due to the curse of dimensionality, if the dimension of R grows, then the success chance is even lower. So random attack is inefficient and should not be considered.
So, but the problem is that, so this reminds me of our Singletel, of their Singletel project. So, but also depends on, so in your case, there's only one boundary in the space, right? So there's a given curse with dimensionalities, but in the real scenarios of deep learning models, there could be a dozens of boundaries around side, or maybe even have thousands of boundaries along the side. And also the boundaries may not be a plane, it might be curved, there will be a curve, right? So in this case, the chances of successful attack will increase.
No, I don't think so. Because
at least better than in this scenario.
No, I don't think so.
Let's make an example here. In your case, you argue that suppose the boundary is like that, the random perturbations will only have half a chance. Suppose I let the boundary like this. So in this case, the random perturbations still can achieve 100% of chance of successful attack. You get my point?
Yes, but it could be that x0 is very far from decision boundary, so you need to guarantee that every time you launch a random attack, you're pointing towards the right direction.
For specifics.
Like you don't reverse, you don't take a reverse step, you don't step back.
What's your point? Mention x is step back.
For example, this is your first iteration, you are here. But that second iteration, you are here. If you just take random, you are just.
But you can see the chances of stepping in this cycle is still small, right?
But I don't think.
Of course. So, because I remember there's some paper mentioning that some random perturbations might still lead to some adversary successful, and a high successful still leads to high successful rate of attack.
I think it's ineffective.
Of course, when we apply the random attacks on our own deep learning models, it does ineffective.
Yeah.
But somehow maybe we can ask Zhang Chen to have a try. When he trained a model of SIP attempts, maybe he can have a try to do the random perturbations to see what's the effect. Okay, please go on.
This is the proof. Do
That's
I
a
need
proof.
to?
I think we leave the proof because we still have another presentation. So the next presentation is Zhang Chen, right?
Oh, I haven't finished.
Okay. Please go on. We do not get to the proof here, but I think I will go through your proof a bit after the meeting.
Oh, okay. So the bad news is that if we don't have any information on the model, we better not attack. But the good news is that usually we can get partial information since the paper or the tool is published. So we usually know the model's architecture, and plus we can query the model. So if we have that, we can launch black box attack. So one typical way of doing black box is that I supply the model with X0, and then the model will output some confidence score, right? Then we perturb X0 and query, perturb X0 again and query to see how confidence score changes. Then we can estimate the gradients based on that. But anyway, black box attack has another set of state-of-the-art methods, which we will not cover today. So finally, let me summarize what I have presented so far. Firstly, I discussed three formulations of white box attack and introduced deep full, FGSM, C and W methods. Secondly, I proved that why random attack is inefficient. Lastly, I briefly introduced black box attack. Okay, thank you.
Okay, so is there anyone have the questions for Rofan's presentation? Okay, if not, let's thank Rofan, and we will ask Zhang Chen for his presentation. Oh, Zhang Chen.
For me, actually, I only read until halfway through section 2.
Yeah, that's what we assign.
Yeah, but I haven't really prepared the slides because the part until I finished reading is just about this defining some of the terminologies and basically giving the background. So actually there's not much basically
so what's the reason? May I ask you a cue? Your explanation didn't even sounds like an excuse.
Sorry?
Your explanation didn't sound like an excuse. I think we assign this paper, and also the reason I ask you to present only half the page is because I gave the paper maybe on this Tuesday, right? Tuesday, I gave the paper on Tuesday, so I just give you 10 page, and this 10 page will be, I think, will be not incur much overhead for your presentation. So may I ask an excuse? Do you have excuse now? Or just do you have, your explanation doesn't even sound like excuse.
Okay. Yeah, but can I do the full presentation next week?
Okay. Yeah. So in this case, I think you need to do the full presentation. So I think that if you have any concern, you just come to me. But if you cannot do the presentations, I can have the other organizations. Okay. In this case, you do the presentations next week, and I hope don't you take the FYP more seriously. Okay. Then in this case, let's call it a day. Thanks, Rofan, for her presentations, and let's meet next week. Bye, everyone.